Hello everyone. Our topic for IDS project is Adult Census Income Dataset. We are building an ML classifier algorithm on the adult census income dataset to predict whether the income of a person is greater than 50k or it is less than 50k. So the dataset that we have chosen has been downloaded from the UCI repository, and it consists of three files. One is the adult.names, which consists the description of the dataset, adult.data, which consists of the train data, and adult.test, which consists of the test data. The entire dataset has 48,842 instances, which consists of mix of categorical as well as numerical attributes. Out of all these instances, the train data file consists of 32,561 instances and test file consists of 16,281 instances. Our data also has various duplicate values and missing values, which we have handled in the pre-processing section. Let's take a quick look at the attributes of the dataset. The attributes of the dataset consist of age, which is a numerical attribute, work class, which may be private, self-employed, and various other labels, FNLWGT. This is a final weight, which is actually the sampling weight from which the sample has been taken from the entire population. Next is the education num, marital status, occupation, relationship, race, sex, capital gain, capital loss, hours per week, and native country. So these in and all are 14 attributes that define our dataset columns, and the predictor or class attribute is the income attribute. So first we load the dataset into the pandas data frame. The language that we are using is Python. So this is the code for loading the dataset into a pandas data frame. The name of the data frame that we have given is test data and train data. This function is going to load the data from this CSV file, and since this data does not consist of any column names, we are replacing the column headers as age, work class, FNL, WGT, and other titles. And our data also has some white spaces within the attribute values, so that are getting replaced using this separator function, and all the missing values are identified as question marks, which are replaced using NA values. So this is the output of the data head. There are total 32,561 instances. So out of these, certain attributes have non-null entries. This means that these entries, these columns have missing values present in them. So the attributes which have less than 32,561 attributes are work class, then occupation, and native country. All of these are categorical data sets, categorical data, and these have been handled in the pre-processing section. So now we'll look at the exploratory data analysis. This section handles the preliminary data analysis of our data set. So first, let us look at the data visualization section. We have used various Python libraries to visualize the data. Now, since our data consists of mixed of numerical as well as categorical attributes, we first look at the numerical attributes, which are 6 in number, that is 6 columns, using histograms. This is because histograms provide better meaning for the numerical data than any other plot in general. So this is the distribution of age, FNLWGT, education num, capital gain, capital loss, and hours per week. It can be clearly seen that capital gain and capital loss are highly skewed distributions having large number of zero entries. So this part will be handled in the pre-processing section of our data. Now we'll look at the categorical attributes using bar graphs. Bar graphs represent count of a particular category or label. Therefore, this kind of graphs, that is bar graphs, will be able to represent our categorical data rather than histograms. So there are 8 categorical attributes. So for each of them we have plotted a bar graph. This is for work class, which is again having high number of private instances. Education, which seems to be an ordinal distribution, since there is an order among the different categories of the education. Marital status, occupation, relationship, race, sex, and native country. Native country is also highly skewed with large number of entries from United States. There is around 28,000 entries. And finally, this is the distribution of income, which can be approximately seen as 75% to 25% distribution, which means that there are 75% of the data in less than equal to 50k range and 25% approx data in greater than 50k range. So this means that our data set is not at all biased data set. So these are the observations in brief that I have already explained. Now let us look at the count plots for the categorical attributes. So count plots are aimed at visualizing 2 categorical attributes, wherein one is dependent on another, or in our case, like occupation is used to determine income, and there are 2 classes of income, so simultaneously we can see the behavior of each of the attribute using this count plot. So we have plotted count plot only for occupation, work class, education, and sex. We also plotted correlation matrix or correlation graph between the numerical attributes, since correlation can be found only between the numerical numbers. So these 6 are the numerical attributes in our data set. So this is a 6x6 correlation graph. This is the scale from 0 to 1, which represents the value of R. We can see that all the elements, all the categories are 100% related with themselves, hence these portions have correlation of 1, and F in the LWGT, which is the sampling weight, is seen with a dark correlation value, which means that this is the attribute which is most not related or uncorrelated with all the other attributes. So we can think of dropping them. So these analysis is used in the pre-processing section to handle the data, so that we can build an accurate classifier. Even the capital gain and capital loss, we saw that they are highly skewed distribution. They seem to be having a very less correlation. So we'll deal with them in also an appropriate manner. Now this is the summary statistics of the numerical data that we have. This is plotted, this is obtained by using traindata.describe, and it consists of 6 numerical columns and their mean, median, count, minimum, maximum, first quartile, second quartile, and median. Now let us look at the data pre-processing section. In data pre-processing, we try to produce data and improve its quality by removing unnecessary or irrelevant material, or optimizing the different values and column number, so that we produce a data which is suitable for training a model and obtaining a very high accuracy on the model. So the first thing that we do in the data pre-processing is data cleaning. Data cleaning is involved with handling the missing values and handling the duplicate values. The missing values are handled using the fill_any function. Now, while loading the data set initially into the data frames, train data and test data, we had replaced question marks using the NA values. So now this fill_any function will replace all those question marks with the mode value of that column. This is done by using dot value counts dot index 0. We are doing this because mode has a good representation of the entire column, since many attributes as seen in the EDS section are highly skewed or have a very high count of a particular category. So now after replacing the missing values, we can see that all the values, the number of values of each of the column is 32561, which is the maximum. It means now it has no missing values. Similarly, we have also handled the duplicate values using the duplicated function of Python pandas data frame. So this finds all the duplicated entries, that is entire duplicated instances or rows, and displays them by marking them as false. Now using the drop duplicate function, we keep only the first unique entry and drop all the further duplicates. The second thing that we do in the pre-processing section is attribute conversion. This is involved at converting categorical attributes to numerical attributes. Now since right from the beginning we have thought of building KNN classifier and training our data on that classifier, we need to take various aspects of KNN and the accuracy parameters which may affect the results of accuracy. So while converting attributes from categorical to numerical, initially we had looked at label encoding method, but it was found that this method was a wrong method. This is because, now first I'll explain what this method does. This method will assign each of the category of a particular categorical variable with some numeric code which is from 0 to maximum categories minus 1 in this range. So this is assigned using .cat codes, and after assigning the codes to each of the variables, we'll get a numerical column. But this has disadvantage in KNN. This is because KNN by default uses Euclidean distance as a measure to find out the distance between data points, and if we are using label encoding method, then we are assigning even the nominal attributes wherein the order does not exist. We are assigning them with some values of different weights, that is different labels, that is 0, 1, 2 up till say 10. So it considers 10 to be a very high magnitude or high weight rather than 0. So it means we are assigning more importance to a label which is now tagged as 10 and low importance to the label which is now tagged as 0. So since label encoding is not a suitable method for our kind of data set, so we move on to one-hot encoding. One-hot encoding converts also the categorical attributes to numerical attributes, but this increases the number of attributes by creating a new column corresponding to each unique label category that a particular categorical attribute consists of. So for example, color is an attribute, and color has, say for example, blue, green and yellow. So a new category, a new column corresponding to blue, green and yellow will be created. Each will have 0 or 1 value, that is a binary value which represents whether an instance has that particular value or it does not have. But now this is represented by an entire new column. So this will increase the number of columns for our data set, but it ultimately will benefit the accuracy results. It is because we are training our KNN classifier on the basis of Euclidean distance. So it will find the Euclidean distance correctly between different attributes. Now as we earlier saw that final weight FNL-WGT is not a very important attribute since it is just a sampling weight. So we will drop this attribute from our data set. Now let us look at the correlation values which might have been created if we had used label encoding. So if we had used label encoding, then by conversion of each categorical attribute to a numerical attribute would have produced all the 14 columns, and this correlation could have been computed. So it shows similar results that we saw previously. Here we can see that education and education num are very closely related with one another. This means that since they have very high correlation, we can either drop one of the columns. But before coming to any conclusion, we'll first look at each of the attributes in detail. So let us look at the first categorical attribute, that is sex. Sex has only two possible values of the categories. These are male or female. Since we have only two different categories, we can assign 0 to any one of them and 1 to the remaining one. This will not affect. This kind of strategy is similar to the one that was proposed by label encoding, but this will not affect our classifier because we have only two values and distance between them remains constant. If there would have been any third column, a third value, then we could have a need to think about what should be the ordering of the numerical label that we are assigning to them. So this is the output that will be produced by replacing each occurrence of male and female within the sex column by 0 and 1 respectively. Now let us look at the next categorical attribute, education. And we also see its relation with education num, since the correlation graph had a strong correlation established between these two attributes. So we can see their column values and we can compare them and conclude that if a particular label of education in the education column has a fixed value of education num in the corresponding education num column, this means that education is just a string representation of education num column. So we can drop one of them. So we have planning, or we will actually drop education num and keep education column and convert it from categorical to numerical. So we have created a dictionary which has been mapped with a unique integer values representing the level of education, and then we have applied this dictionary on the trained data's education column. This will convert the values looking from the dictionary into an integer values, producing a numerical column. Next is the work class attribute. Work class has 8 unique categories which we will relabel or group them to produce only 4 labels, that is 4 categories. Now the 4 categories that we are assigning are not working, self-employed, private and government. Now we should also assign a unique numeric label to each of these 4 categories so that Euclidean distance can assign or find the distances between data points using different priorities. Now since not working is highly different from all the other working categories, we'll assign it the least priority of 0. Then highest priority is assigned to 10 because it has highest number of instances, which is over 20,000, which means most of the people are engaged with the private work class. Next, self-employed is similar to private, so we have assigned a categorical value, numeric value equal to 9, which is very close to 10, and government, which is very far from not working, but it should have been carrying a value which is less than 9 or 10. So we have assigned it 7. By applying these values, which have been represented or done through a dictionary, we can produce numeric columns of the work class.
Now we will do one-hot encoding on marital status and relationship. Marital status attribute has total 7 distinct values. So we will regroup them into 4 distinct values with assigning new labels to some of them. We have assigned the new labels in the following way using dictionary in Python. So we have mapped the values such that the total 7 distinct values are converted into 4. After this, we have merged the marital status and relationship because they combinedly can better determine the classifier or the class attribute. So we have merged them using this function, using this function in Python, and after that we have used one-hot encoding on that combined column whose name is marital relation. So after combining them, we use pd.getDummies, this function, to use or to apply one-hot encoding, and after applying one-hot encoding, each of the attribute will be converted to a new column as explained earlier in the presentation. After this is the output that we will get. In this following way, we will get the new column name as marital relation, widowed, other relative. Following is the count plot for relationship and marital status attributes. So this is the marital status and this is the relationship. We can see that they are not very we can see that for never married we have not much for husband, not much data for husband. Similarly, the data attributes are very less. So in case we merge them, the total number of unique attributes will be less, because corresponding to married, like we can see other relative are very less. So we can ignore all of them and the total number of unique attributes will be comparatively less. Hence we have done one-hot encoding on the merged column, that is marital relation. Now coming to occupation. Occupation is the categorical attribute. So we have done the grouping similarly similar to the above in occupation, and then we have applied one-hot encoding. After doing the mapping like this, we have applied one-hot encoding using the same function as above. This is the output for occupation. Now we will talk about native country column. Native country is also a categorical attributes which we have to convert into numerical attributes. So by converting native country into numerical attributes, what we did was we stored the GDP of every country in 1990s, so exactly in 1994, the time when this data was taken, into a dictionary. Now this dictionary contained all the GDP values. We divided this dictionary into 3-4 parts: 0 to lower quartile, quartile to median, median to upper quartile, and upper quartile to all above. And then we reassigned the values in the dictionary to 1, 2, 3, 4 corresponding to these quartiles. After this mapping was done, now dictionary contains the following 1, 2, 3, 4 corresponding to the GDP. So suppose it lies in 0 to lower quartile, the GDP will be assigned 1. Now we have to map this GDP, this dictionary, to our train data column, to our native country column in train data frame. So for that, what we did was we just use a function for map dict dictionary. This name of the dictionary is dict map nat country. In this way, we have converted the value of all the categorical attributes to a numerical attributes, to the numerical one. This will be the output. So most of them are 4 to, all of them will be 4, between 1 to 4, like this. Now we will be handling skewness in capital gain and capital loss. So they were right skewed, and we handled them similar to what we did in native country. So we assigned them all those lower quartiles and corresponding values of 1, 2, 3, 4, and after applying this, we got this as the output. So the skewness was decreased as compared to original skewness. Now we did the feature selection. In feature selection, we removed all the attributes which were irrelevant or not required for to classify the class attributes. For those 3 attributes were final weight, education num, because education and education number was highly correlated, which was already explained earlier, and we also dropped the race attribute because it doesn't seem to be important attribute to determine the income. Now we did the normalization. For normalization, we use the following function, preprocessing.normalize, and we mentioned the data frame. After doing the normalization, what normalization did was it converted all the values, it scaled all the values in from 0 to 1, so that there should, if there is any skewness left in the data set, it will be removed, because all the values will lie between 0 to 1 after applying normalization. In this way, we have applied the normalization, the code in the Python is in the following way.
Now let's look at the final section of the IDS project. This is model training section. In this section, we train our model with the KNN algorithm. We have used train and test data files to train our model. So first we split the data sets into xtrain, ytrain, xtest and ytest using this piece of code, wherein xtrain and xtest are the class attributes, non-class attributes of the train and test data sets respectively, and ytrain and ytest are the class attributes of the train and test data sets respectively. Now let's look at why we chose KNN and how can we improve it. So KNN was chosen by us because all the members of our group found it interesting, the working of this algorithm, and we thought of implementing this algorithm on our model. Even the data set of ours is a very large one, that is, it consists of 48,000 instances. So we thought of making the entire process of training to be faster. So this KNN serves our purpose. Training phase of KNN is much faster as compared to other classification algorithms. There are various other key issues related to KNN which have been mentioned in this section, and these issues have also been appropriately handled by us in the pre-processing and cleaning section previously. For example, KNN requires normalized data since it uses by default Euclidean distance to find distance between two data points, and Euclidean distance finds a distance based on the weights or magnitudes associated. So if the magnitudes of two columns are highly different, then it will affect the accuracy. Similarly, handling missing values is also an important part to increase the or enhance the accuracy of the model. So we have handled the missing values also. One of the disadvantages of KNN is that it's not suitable for large dimensional data. But the initial data set had 14 attributes, that is 14 non-class attributes, and after pre-processing and cleaning, the final data set had 33 non-class attributes. Although we have increased the number of features, but we have established and produced a clean data set having a good relationship and understanding for the KNN model, so that it can apply Euclidean distance and other measures in an appropriate manner. This disadvantage of having a large dimensional data set is called curse of dimensionality, which will affect the model. But this large dimensional data means it has hundreds or thousands of features. However, we only have 33 features before training, or for training the data. Our training data has only 33 features. So this should not affect our accuracy, and KNN should work perfectly fine. Choosing the distance measure. There are various distance measures available like Hamming distance, Euclidean distance, Manhattan distance, or Minkowski distance. Hamming distance is used for binary vectors, Manhattan for real valued attributes or continuous values. However, our data has mostly integral values in a particular range because we have converted most of the categorical attributes to numerical attributes. So in this kind of data set, Euclidean distance plays a very important role, and it should be an apt measure for achieving a good accuracy. Choosing the value of k. Now value of k, if it's small, then it means that noise will have a higher influence on the result, and if it's high, then it means that the entire process will be computationally expensive. So according to some research mentioned in this pattern classification book, we have chosen the value of k to be root n, which will produce a good accuracy. Now we'll train the classifier. We have imported neighbors from sklearn library, and we have used its function .kneighbors classifier to build a classifier CLF. Now we also pass a distance measure in the form of metric equals to Euclidean or some other metric if it is to be used. If nothing is passed, then it by default assumes the distance measure equal to Euclidean distance. We also pass the value of k in the algorithms in the functions parameter list. So we have passed n neighbors equals to 180, which is approximately the square root of 48,000 rows or instances that our dataset consists of. Now using clf.fit function, we'll fit the train and test xtrain and ytrain datasets into a classifier and build the classifier, and we'll predict the accuracy using xtest and ytest using the clf.score function. Since it's using Euclidean measure, we have also scaled the data sets or data values before training them using the fit function or predicting the score function. So the KNN classifier produced an accuracy of 82.507%. This is the terminal output. Now we also compared our result with some standard research. So one team from Institute of Technology Blanchard Stone, under supervision of Marcus Hoffman, submitted the research on adult datasets on 21st of May 2011, and the things that they performed as a part of transformation or data preprocessing on their data consisted of following things. First one is discretization. Discretization they performed on the attributes hours per week and age to classify them into 2 bins and later into 11 bins. Another thing that was done by them was dropping of irrelevant columns. So they dropped country, education number, final weight or survey weights, and marital status columns. They also handled the missing values. Rather, they removed them, and their KNN that they used was built using the value of k equals to 159, and the accuracy that they obtained was 85.33%. We can conclude that the difference in the results might be because of these reasons, that they have dropped marital status and country column, however, because they might have thought that these columns are not good predictors of the income, however, and actually they might also be true, but however we have considered these two columns. Even our value of k is approximately equal to 180, and we have not discretized the columns hours per week and age, which is done in their research. Thank you.